Okay, today we're going to work on net ionic equations, and the thing is, it's related to what we've been doing in the past with chemical reactions. There are equations that only occur in solution. That means things that are dissolved in water. And you know, you guys, well, I did a lab that you guys then completed on your own, but you know, I did some double replacement reactions. They were all in solution. Some single replacement reactions as well, where you put a solid into something that's dissolved in water and you watch what happens. So anyway, so like I said, there's single, double replacement reactions, and net ionic equations is really just a way to simplify equations. We just didn't show you how to simplify them a while back, and so what you do is you only include the substances in the reaction that are actually involved in the reaction. There are what are called spectator ions that are not involved, and you don't have to include those. So really, we're going back, like I said, we're going back and showing you how you can simplify some equations. But you do need to remember that when you're talking about double replacement reactions, what you're looking for a double replacement reaction to occur is you're looking for a product that is insoluble in water, something that makes a solid in water. And there are actually, when you talk about how you know a double replacement reaction occur, there's one of three things has to happen. One, you get an insoluble solid, which is called a precipitate. We use this solubility chart to do that, which we're going to practice on in a second. Or if you get water as a product, the reaction occurs. Or if you get a gas, which the only two gases were SO2 and CO2. But you do have to remember that if you get water as a product, this chart, you can't use it to find that. And if you get SO2 and CO2, it doesn't help us either. But again, we're going to get a little practice again looking at solubility rules to determine whether or not something would form a precipitate. So AgNO3, again, the way you use it, it's got the negative ion first here. So NO3 and any positive ion is soluble. So when you're labeling that, that would be AQ. Now this, if this happens, something that's soluble in water, it's not reacting. Nothing's happening. So that's really not what we're looking for to determine whether or not a double replacement reaction occurs. We're looking for a solid or a precipitate to occur. So K2CO3, again, there's carbonate, and alkali ions are on the first column. Those are called the alkali metals in column 1 on the periodic table, and potassium is one of those, so that's soluble as well, so that would be AQ. Calcium phosphate, there's phosphate. Calcium is not in column 1, it's any other positive ion, so it is not soluble, so that would be a precipitate. Silver chloride, there's all the chlorides plus Ag, not soluble again, so that would make a precipitate. Sodium hydroxide, and hydroxide in alkali metals, which is what sodium is, and it is soluble. So again, just a little practice using this because that's what you have to do to complete net ionic equations. So let me show you how to do 3 problems, and then you can work on them on Go Formative. So here you go, first one. Nitric acid, barium hydroxide. Now I would not expect you to know the formula for nitric acid. We haven't talked about those. I would always give that to you. And barium hydroxide, but nitric acid is HNO3. Barium hydroxide, you would need to know how to put that together. Barium is in column 2, so its charge is +2. Hydroxide is a polyatomic ion with a charge of -1. Remember, if you bring a number down larger than 1 below a polyatomic, you got to put it in parentheses first. And so there, we put that together properly. Now remember, when you're dealing with double replacement reactions, you put the positive ions with the negative ions, which means you put the insides and the outsides together. So in this case, we put H and OH together. You cross the charges, you get HOH, which is the same thing as water. And this reaction then occurs because remember, if you get a precipitate, something that's insoluble, if you get water, CO2 or SO2, the reaction occurs. So we don't need to use this chart for this one because we got water as a product, so we know that occurs. And then we know obviously it's a liquid there. And then we get barium nitrate, and you can look that up. Any nitrate with anything is soluble, so nothing happens there. So this reaction occurs because of that. That's what happens there. And so then we've got to balance this equation. So we'll do that, and we've got 2 hydrogens there, a third one there. So we got an even odd situation. We're going to have to put a 2 there. And and let's see, we're going to put a 2 here, and then that balances that equation. So you always have to go back and balance it. 2 hydrogens there and 2 more, there's 4, so there's 4 hydrogens. There's 2 nitrates here, 1 barium, and again, we already balanced the hydrogens and oxygen. So that is our balanced molecular equation. So again, I should draw an arrow so you know where it is. So a complete ionic equation. You pull everything apart that dissolves in water. Now, when you're dealing with double replacement reactions, the reactants will always be soluble in water. These things cannot happen, so there's no need to look them up. They're soluble in water. So what water will do is water will pull apart anything ionic that you drop in there. Actually, it's a generalization to anything. It's not always true, but most of your ionic compounds will dissolve in water. So you got to look at what water's going to do, though. So water's going to pull this apart into 2 hydrogen ions. There's 2 of them that have a +1 charge. And so there's 2 of those total molecules, and so it'll also produce 2 NO3s, which have a -1 charge. Okay, when you drop this in water, because all these things, these reactions, they start off in water. They don't occur any other way. So these are things that would be dissolved in water. We mix them up and see what happens. And then we get, with the water then, we also get water as a product for this reaction to occur. Over here, we got barium. It gets pulled apart in barium with a +2 charge. And there's 2 hydroxides that pulls apart. And again, water's going to pull all of these things apart. And then over here, again, it doesn't pull itself apart, so you get water, which is a liquid, so that stays together. And these things, again, are soluble in water. Again, if you go, well, how do you know that? You could look it up if you wanted to, barium. And you could look up the ones that are the reactants. You would find that they're soluble as well. So nitrate, any positive ion, soluble. So water pulls them apart into their ions. So there's a barium with a +2 charge. And it pulls apart into 2 nitrates there. So individual nitrates there, it pulls them all apart. So that's, again, our complete ionic equation. A net ionic equation, though, if nothing happens to whatever the compound or element from left to right, if it doesn't change its charge, or if it doesn't change into a liquid or a solid, you don't have to put it in the equation. Over here, hydrogen, there's 2 hydrogens with a +1 charge, and over here, it's part of water. So it's a liquid there, so it changed. Here you got 2 nitrate ions here, you got 2 over there, get rid of them. If they don't change from left to right, you get rid of them. Barium is dissolved in water on this side. It is also dissolved in water over there as an ion, so get rid of that. And then the hydroxides formed water, so that's what changed. So our complete net ionic equation then is 2H plus 2 OH ions over here that actually came together and formed 2 water molecules. And again, the equation is balanced. The charges are balanced. There's no charge over here, no charge over there. The total the total number of atoms and ions are balanced as well. So that is our net ionic equation. We only included what happened that actually caused that reaction to occur. All right, this one here, just want to point out real quick, when you look at all this, this is NaCl, this is NH42SO4. When you look at the possible combinations of Na2SO4 and NH4Cl, nothing happens. So again, sodium sulfate, any other positive ion soluble, ammonium chloride, ammonium is any other positive ion soluble. So there's no reaction in this one. Okay, so you need to be aware. You always got to look up the possibilities in a double replacement reaction to see if that reaction actually occurs. All right, so we got 2 more, and then I'll let you work on some on formative. So first of all, we want a balanced equation. You put strontium chloride together, so that's SrCl2. And across the charges, strontium's in column 2. Sodium sulfate, sodium charge is 1. Sulfate is SO4 with a 2 charge, so you bring the 2 there, you get Na2SO4. And then our possibilities for products. We know it's a double replacement reaction because it's 2 compounds. They would again be dissolved in water, so they're aqueous. The reaction couldn't start if that wasn't the case. And then what we get is strontium sulfate, and they're 2 and 2, don't do anything there, and sodium chloride, and we do need to balance it. Going to need a 2 there to balance that, and let's see, that's it there. But we need to see if this reaction actually occurs. So we use our solubility chart. Sulfate, strontium, not soluble. There you go. So that's a solid when you put it in water. So it sticks together. Water cannot pull that apart. This one, you don't need to look it up. If this one's a solid in water or precipitate, the other one's going to be dissolved in water. All right, so there's our equation. It is now balanced. Our complete ionic equation for this, again, you pull everything that would be aqueous in water or dissolved in water, you pull it apart because that's what happens to it when you put it in water. So water makes that strontium. Again, you put the charge, it actually has a +2 charge, so there's one strontium ion that water would pull apart. It means it's lost 2 electrons and +2 there. And water's going to pull it apart into the individual ions there. So those chlorines are not going to stay together. There's going to be 2 chloride ions there that water will pull apart. And again, if you go, how do I know that? Because it's aqueous in water. Water's going to pull it apart into the individual ions that it has. And then this one also would be dissolved in water, but water will pull everything apart there. Cannot pull apart the insides of a polyatomic, but it can pull apart the metal and the polyatomic ion. So there would be 2 sodiums here. Again, there's 2 of them. Water. This means they're stuck together, but as soon as you put them in water, water's going to pull them apart into 2 different sodium ions. And also you'll get that sulfate ion as a -2 charge. Again, like I say, water cannot separate those covalent bonds that are in that, but it can. That will dissolve in water there. All right, on the other side, remember, strontium sulfate, we've determined it's insoluble. So water can't pull it apart. So that's what's actually reacting there. We would see that it would be a precipitate. I don't know if you remember those reactions, but they suddenly change colors when I mixed them together. And then salt will dissolve in water again. So what would it be? It would be 2 sodium ions there and 2 chlorine or 2 chloride ions, because again, it's aqueous. Water pulls it apart into individual ions. So that's our complete ionic equation. And then all we have to write are net ionic equations, like what actually occurred, what changed. Strontium +2 over there, again, it's in a compound over here. 2 chlorine ions there, nothing happened. They stay dissolved in water. 2 sodium ions here on both sides. That didn't change either. That's +1. So what changed is sulfate ion here was dissolved in water, but now it's stuck together with strontium on the other side. So our net ionic equation is Sr +2, SO4 -2, produce Sr, SO4, and again, it is a precipitating water. So that was what reacted. That's all we include in these equations. And these equations also work for single replacement reactions. When you put a metal into a solution of a metal in another compound, these reactions occur if the metal by itself is higher on the activity series than the one it's trying to replace. And I don't have one printed out here, but again, just looked it up on my phone. Copper is higher on the activity series than silver, so it'll knock it out of the way and replace it. But again, so these reactions occur, the element by itself is a solid. So it'd be solid copper metal. And this is just when we're talking about single replacement reactions. You would again have an element, you always have an element here and a compound, and this element would always be a solid in a single replacement reaction, and the compound you start with would always be dissolved in water. So this is what we start with: copper and then silver nitrate. Their charges are 1 and 1, and it would be dissolved in water. And so for this reaction to occur, like I said, copper's got to be higher on the activity series than silver. It knocks it out of the way, and what it makes is copper nitrate. And we're going to assume there that the charge of copper is 1. It could be 1 or 2, but we're going to say that it's 1. And then silver gets kicked out, and that makes, again, it gets kicked out and becomes a metal. And so over here, it's dissolved in water as an ion, and over here it becomes a silver metal. And so this product here, you can look it up. Any nitrate ion is dissolved in water. So so we had this metal replace this ion in water, and then we ended up now with copper nitrate being formed and silver metal. And so now we need to balance that equation, and it's already balanced, so there's nothing to do. So that is a balanced molecular equation. So our complete ionic equation, this is a solid by itself. Copper is a solid. These reactions, it would have to be copper metal that we're starting with if it's a single replacement reaction. Again, single replacement reactions, this is the case. Whatever you're trying to put the metal in has to be something that's dissolved in water. So that solution there is water pulls that apart into silver ions. and nitrate ions. And then what we got over here was, again, copper was higher up on the activity series than silver. It knocks it out of the way, and it forms another compound that is dissolved in water. And again, if you go, well, can I look that up? You could look it up on the solubility chart to see that copper nitrate is soluble in water. You get copper ions plus nitrate ions, and then copper knocked that silver out of the way, and now it becomes a solid. So the silver would precipitate out in solution. And this would be easy to see. You know, if you look up, if you look up this reaction, like on YouTube or something. Again, obviously the copper is a brown metal. This would actually be a blue or silver nitrate. No, I take it back. It'd be a clear liquid. Silver nitrate would be a clear liquid. I got ahead of myself there. I was thinking, and as soon as copper nitrate is formed, that's actually a blue. That would have a blue tint to it. And then silver metal would be obviously shiny silver color. And so it'd be easy to see that this reaction is occurring and what's actually going on there. So again, when we do a net ionic equation, though, we only include those things that actually changed. Copper went from being a solid here to an ion there. It changed. Silver went from being an ion here, it dissolved in water, to a solid over here. It changed. The nitrate ions, though, they were nitrate ions on one side and nitrate ions on the other. So again, the only thing that happened here, you had solid copper and silver ions. Before you mix them together, the copper knocked silver out of the way and actually dissolved with nitrate or combined with nitrate, and then you ended up with silver metal. And again, those are your how to complete double and single replacement reactions, and a way to simplify them. You only include the things that actually react or change in that reaction. And so you'll have something to work on. Go formative. Good luck.